or the quotient rule? We left off on, we're on example 5. Evaluate each of the following. So we've learned the product rule, we've learned the quotient rule, and as we saw in yesterday's warm-up, we can combine them along with the power rule and the sine and cosine rule. So when you walk up to this problem, it says to take the derivative with respect to x. Do you see a product first or a quotient first? What's the rule that you're going to use out of the box? It's a quotient. You got something divided by something. Now, of course, you could use the associative property of multiplication to rewrite it if you want to, but I don't see any need to do that. So if we're going to take the derivative using the quotient rule first, we go ho. Are the parentheses required there? Yeah, it's more than one term. D high. Now, D high is going to require the what rule? Product rule. So here we go. The derivative of x is 1 times sine of x plus x times the derivative of sine of x, which is cosine of x. And there you go. There's D high. So now that we have ho D high, product rule inside the quotient rule, we can finish the quotient rule. Ho D high minus high, which is x times sine of x, times D ho. What's D ho? The derivative of x plus 1 is 1. So you don't really need to write it, but I'm going to go ahead and put it for inventory purposes. All over ho ho or ho squared. So notice in this case I'm working straight down because I'm really just starting with an expression. It's in the verb format, and once you take the derivative, the d dx goes away. There you go. The calculus part of the problem is over. What's left? Maybe a little bit of algebra, right? Combining things. I'm not sure if I want to do this, but let's see if we can just make it look a little prettier. That's sine of x plus x cosine of x minus x sine of x all over x plus 1 squared. Can I divide out one of those x plus 1s? One of those with one of these? Those divide out? No, because it's not a factor in the top of both terms. The only thing I could do in the top is expand, right? You want to FOIL it out? We might as well. I'm noticing here that if I just do this right here, I'm going to get an x times sine of x term. Y'all see that? And what do we have sitting there at the back in the numerator? A minus x sine of x. So those are going to be able to cancel. So this might be worth it. If I distribute, I get x sine of x, plus distributing the x to the next term, I get x squared cosine of x. And then I move over to the 1, and I get plus sine of x and plus x cosine of x. So I don't like to call it FOIL. I certainly don't like to call it saran wrap. I just like to call it distributing. And then we have minus x sine of x there at the back. All over x plus 1 squared. Now, why do we do that? Well, to see if we can combine anything. And as I anticipated, these will cancel. And then does anything else combine? Not really. You could group your x cosine x terms together and factor out an x cosine x, but I'm not going to do that. Nothing else is a like term. So for now, we'll just stop right there. There will be a time where we're using these derivatives, and then we'll decide if we want to keep going or factoring it out. So as you're going to see with a lot of these problems, the calculus part's the easy part. It just takes up one line. Sometimes you have to rewrite beforehand. Sometimes you have to clean up afterwards. The calculus, the Hody-High rule, the product rule, that's the easy part. Okay, so looking at this one here, you walk up to the problem, and what do you notice right away? A product or a quotient? I see something times something. Yeah. Now, again, you could rewrite it and do it a different way, but let's just go ahead and do it this way. The derivative of the first factor goes first, right, in the product rule? And that's going to require the what? Hody-High rule. So now it's a Hody-High inside of a product rule. So doing the Hody-High rule, we get ho. And what's D-high? 1. So times 1. That's Hody-High. Minus high is x. D-ho is 1. All over ho-ho. So there's the derivative of the first factor times the product rule says just the second one, yes? Plus, now we just write x over x plus 1 times the derivative of sine, which is cosine. So notice the product rule gives us two terms. The quotient rule gave us a single fraction with multiple terms in the numerator. Let's go ahead and see if we can clean this up a little bit. If I distribute the top, I get x plus 1 minus x, and that's really sine of x over 1, so I can multiply it by sine of x all over x plus 1 squared. That's the first term, for starters. And the other one, that's really a cosine over 1, so I can call it x times cosine of x all over x plus 1. Now, of course, what happens in the first term with your x's? They cancel, and you're just left with 1 times sine over sine. So we have sine of x over x plus 1 squared plus x cosine of x all over x plus 1. Now, you could stop there. That looks like it's cleaned up pretty well. But if we were interested in getting a common denominator so that we can combine the two, what would be the LCM of your denominators? X plus 1 squared, yeah. So the second factor would need an extra x plus 1 factor. So if we multiply by a clever form of 1, that should be legal, yeah? X plus 1 over x plus 1. And now if you multiply it across, you'd have x plus 1 squared plus x plus 1 squared. So as I tell my daughter at home, go ahead and build your shelf first, now that you know you have a common denominator, and put it over that common denominator, and then work on what the numerator will be. You'll have sine of x plus, let's go ahead and distribute. You get x times x, which is x squared cosine of x, plus times 1, you get x cosine of x. And it doesn't look like any of that combines. So we're done. Now, did that have a deja vu kind of feel to it? Notice what we did on example 5A was really the same thing we did on example 5B. I don't know if you picked up on that. They were equivalent functions to start with. The difference on A is we had x times sine over x plus 1. On part B, all I did is I associated the x over the x plus 1 as a single factor and kicked sine off to the side, right? If you call that sine over 1, you get the exact same function. So if we do the exact same function by using different methods, should we end up with equivalent answers? Yeah. Now notice in the short run, we ended up with very different looking answers. Again, the quotient rule will always give you, when you implement it, it'll always give you a single fraction. Keep that in mind as we go forward, because a lot of the times it's nice to have a single fraction, because when we set it equal to 0, we can analyze the numerator and denominator separately. Whereas the product rule will always give you two terms, which if you were then interested in making it a single term, you would have to get a common denominator. Now, if we compare the bottom lines on both sides, are they in fact the same, but for the terms being written in a different order? Yeah. So isn't it nice to do something two different ways and have it work out? Maybe. Choices, right? So when you come to that fork in the road, take it, yeah? You're going to have options. Okay, are you ready to learn the derivatives of the other, I guess I should just say 3 trig functions, because right now we know the derivatives of 3 of them, right? What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. And then, of course, we kind of snuck up on deriving the one for tangent. What's the derivative of tangent? Secant squared. So we know 3 of them. You want to meet the other 3? They're dying to meet you. All right, here we go. Bless you. Derivative of tangent is secant squared. Guess what the derivative is of secant? Don't look. Oh, actually, you have to look. I guess you don't know what it is. The derivative of secant is, guess what? Secant times tangent. The derivative of secant is secant times tangent. What's the derivative of secant? Secant times tangent. These are the two that students tend to get confused. They sometimes want to say the derivative of tangent is secant times tangent, but it's not. The derivative of tangent is secant times secant, if you want to think about it that way, right? Or secant squared. The derivative of secant is secant times tangent. Now, if you have these two memorized, and I hope you do, the other two essentially come at no additional cost. How much do these cost you? $0, right? They were free. So I guess I should say that the other two come at 10 times the cost, right? Yeah. Ooh, that sounds expensive, right? But what's 10 times 0? 0. They're still free. All right. If the derivative of tangent is secant squared, then guess what the derivative of cotangent is? Cosecant squared, yes, but of course, because it starts with co, as I promised, it's also what? Negative. It is negative cosecant squared. So all you did was add cos in front of both of them, right? Instead of tangent being secant squared, it's cotangent, cosecant squared, and of course it is negative. Does it work also as well for secant? Well, let's see. What would you think then the derivative of cosecant would be? Cosecant times cotangent, of course, being negative. Let's see if it's true. It's true! The derivative of cosecant is negative, of course, because it starts with co. Cosecant, cotangent. You just put cos in front of everything. Don't that amazing? It sure makes it easy, don't it? Yeah. Okay. It says, memorize these if you haven't already. Who hasn't already memorized them? Don't raise your hand. Let's try it. Let's get rid of this. What would the derivative of tangent be? Secant squared of x. Good. And what would the derivative of cotangent be? Yes. So we usually say negative cosecant squared of x. Yeah, but you're right. Negative cosecant squared of x. Good, good, good. And what would the derivative of secant be? Yeah, tangent x, secant x, or secant tangent, right? Yeah, or tangent secant. Multiplication is commuted. So the derivative of secant is secant tangent, and the derivative of cosecant, Mr. Reed. Negative cosecant, cotangent. Yeah, good. Cotangent of x. Good. Very good. Very good. So all three cos, cosine, cosecant, cotangent, they're all what type of answer? They're all negative. Yeah. And all the ones that aren't co are not negative. Guess what? We now have expanded our derivative toolbox set of tools. Huh? All right, let's try out these new things. Huh? Yeah. Find the derivatives of each of the following using your memory. All right. The derivative of g of x, if g of x is x minus tangent x. So you walk up to the problem and you're like, hey, I spy two terms. You get excited, right? Because that's two problems in one. Every time you see a term, it's like its own individual problem. Do any of those terms need to be rewritten? No. So we can jump straight to the derivative. What's the derivative of the left side? Don't forget the left side. G prime of x. You'd hate to lose points for the easy part. What's the derivative of x? 1. Minus, what's the derivative of tangent? It becomes secant squared, right. So because it's minus tangent, it becomes minus secant squared. Yeah, excellent. Perfect. Now what if this were a multiple choice question, and that was not an answer choice? Would you panic? Would you panic? Say no. No. What? No, because that's the constant rule. Remember, if you're taking the derivative with respect to x of negative tangent of x, that's like negative 1 times tangent of x, right? And we have the constant rule that says that's the same as negative 1 times the derivative with respect to x of tangent of x. It's the same reason if we were like 5 sine of x. What's the derivative of 5 sine of x? 5 cosine of x. You'll see that constant multiples go along for the ride. It's not a variable function. It's a constant. So they go along for the ride. But whenever you see a number 1, especially with a squared trig function, your mind should take you back to a certain family of identities. The PIDs. Let's review the PIDs, all right? You have Papa PID with 2 P's in the middle, 3 P's total. Papa PID. Why 2 P's in the middle? That's how he spells it. Cosine squared of x plus sine squared of x equals 1. And then you got baby PID number 1. Baby PID number 1. You don't have to worry about their names. If you divide everything through by cosine squared, you get 1 plus tangent squared equals secant squared. And then baby PID number 2, if you divide papa PID by sine squared, you get 1 plus, and this is almost as nice as memorizing the derivatives, right? Tangent squared becomes cotangent squared, and secant squared becomes cosecant squared. You just change those to cos, and you got the other one. So those you should know. So what is another way to say 1 minus secant squared? Negative tangent squared of x. Good, because you can manipulate that equation. And that makes for maybe a better multiple choice answer because it's easier to type, right? One less term. And it requires you to go one step further, which is always good. Unless you're already at the edge of the Grand Canyon, then one step further. You don't really need to experience the Grand Canyon like that. Okay, there is a limit, right? You try. On your mark, get set, you try. Go. Find dy dx. I'll start you off on the left. Dy dx equals. You're welcome. Use any and all derivative rules that you've learned. And remember, it's always an option to go back to the limit definition as h goes to 0, but I would not recommend it. I would highly not recommend it. Product rule. You took the derivative of both at the same time. So one at a time. Bless you. One at a time. Product rule, right? You did both at the same time, one at a time. Good. You did one at a time. One at a time. Bless you. One at a time. Is there assignments today? You'll have a test today, I'm guessing. Test. One at a time, one at a time. One at a time. Good. One at a time. One at a time. Huh? That's just A times B times C. So there's no distributing. It's not, yeah, that's it. It's just x secant tangent. Yeah. One at a time. One at a time. Oh, you did them both at the same time. One at a time. If there were a plus sign in between those, like there was in the previous problem, you could take the derivative of each one independently and just string them together with plus or minuses. But this is a product rule, right? And remember, there was an incorrect product rule. And some of y'all were doing the incorrect product rule correctly, but albeit it's still incorrect. So if you have two factors, you should have how many terms? 2. So the derivative of x is 1 times the second goes along for the ride, right? 1 derivative per term. Plus, now it's secant's turn to go, and the derivative of secant is secant x times tangent of x. And you're essentially done. You could factor out a secant if you preferred. Thinking about later on what we might want to do, that would be 1 plus x tangent of x. But for now, you don't even need to do that. All right, so I told y'all back in the day that the product rule is the one that students tend to mess up most frequently. Just take inventory before you start, right? I have 2 variable factors. I'm going to have 2 terms. If you had 3 variable factors, you'll have 3 terms. And you just do 1 derivative per term. Everything else gets rewritten. All right, example 7. Differentiate each of the following, then show that they have equivalent derivatives. Okay. Derivative first. All right, so here we go. Walk up to the problem. What do you see first? I spy a quotient. Anything need to be rewritten? I don't see it, so here we go. F prime of x is ho. Do we need parentheses around ho? Doesn't hurt, but it's 1 term, so you don't necessarily need them. But ho d high. What is d high? What's the derivative of the high function? The 1 goes to 0, right? And because the derivative of cosine is negative sine times the negative that's there in front, it becomes positive sine. Yeah. So there's ho d high minus high. Now we need parentheses, yes? Because the high function is 2 terms. And then what's d ho? Cosine. All over ho ho, which is sine squared. Remember, when you square sine, you write it between the n and the x. Now, I'm going to stop right there because what this says is to differentiate the following and show that they have equivalent derivatives. I think there's some simplifying I can do at this point, and there's probably some trig identities that I can use as well, but I want to go ahead and find the derivative of the other side first so that I can have a target. If I'm trying to show that the results are equivalent, I need to see what the results of the other one are first, yeah? Before I get too far. So, whoa, this one's cosecant minus cotangent. How can the derivative of that be equivalent to the derivative of that? They don't even seem like they belong in the same family, do they? They're dramatically different. I don't know. Let's see. Anything need to be rewritten for this one? Written again? Y'all are already ahead of me, aren't you? What's the derivative of cosecant? Negative cosecant cotangent. Good. And then the derivative of cotangent, of course, will be negative something times the negative that's already in front of it makes it positive. And of course, it would be cosecant squared. So it's negative cosecant squared, and the negative that's already there turns it to positive. Okay, so what the question then asked us to do is to show that this right here is equal to this right here, which means now we're kind of back in pre-cal, and we're trying to do this tiny little trig proof. Oh yeah, trig proofs. Love them, love them, love them, love them. On which side should we start, the left or the right? The left, because it has more information, right? Remember, it's easier to tear down than to build up. So the left side is already in terms of sine and cosines, but there's a couple things I could do over here. So sine times sine, we can call that sine squared of x. Here I got to distribute a negative cosine, and this is the real peril in the quotient rule when you're expanding, because you're distributing a negative from the front and something that's possibly in the back, d high from the back. So you get a negative cosine of x and then a positive cosine squared. Negative times negative, all over sine squared. Now, if I write the sine squared right there, directly into the other sine squared, do they divide out? No. No, they don't. So don't do that. But anyone see anything after this point that we could do? Well, the sine squared and the cosine squared are both positive, but even though they're not written side by side, I know by the associative property I can, and then I can call them what? 1. That's Papa Pid, right? In the house. So it becomes 1 minus cosine of x all over sine squared of x. Now from here, you might want to take a look at the other side, right? Keep your eye on your target. If you don't know where you're going, any road will get you there. We have a destination in mind. What would you do at this point last year? Would you keep trucking on the left-hand side? You might jump to the other side and say, hey, when in doubt, put everything in terms of sine and cosine. So let's do that over here. That's negative cosecant. That's the same as negative 1 over sine. Cotangent is the same as cosine over sine. It's a great way to review our ratio and reciprocal identities. And then cosecant squared, why, that's 1 over sine squared. Now I have 2 terms over there, and I have 1 term on the left. And remember, one of the strategies was to get a common denominator to combine 2 terms into 1. Do we already have a common denominator? Yeah, we already have one. It's sine squared. So build the shelf. And what goes in the top? Well, we have a negative cosine plus 1, but I'm going to call that 1 minus cosine. Oh, yeah, let's look at that. Did I just make a careless mistake and lose some points? Yeah, I sure did. If you're going to do it like that, of course, you either need to have parentheses there or just say, that's not the way that I want to present my work. Thank you. There you go. Now, if you look at what's over here, are we there? How did I do that? Okay, let's do it. This becomes a negative 1 times cosine, so that's negative cosine of x all over sine times sine of sine squared. plus 1 over sine squared. And then that's sine squared. Yeah, and then because now I can add them, negative cosine of x plus 1 is the same as 1 minus cosine, just by the commutative property, as long as the negative stays with the cosine. And now these two are the same, so remember what we did at the end of our proof? You signed off, right? And mathematicians usually put QED, but I always favored sizzle. Just my favorite. Sizzle on fire. Huh? QED is Latin for quid erat demonstratum. And it's just a fancy Latin way to say, I did it. I did it. I'm done. Would it? QED? Why would it make a physicist mad? Oh, the QED theorem? Does the QED in the quantum theorem not stand for quid erat demonstratum? No? This just means that which has been demonstrated. That which has been demonstrated. It just means I did what you asked me to do. I showed it. Yeah, we don't want to anger any physicists. Okay, I want to bring people together. All right. Anybody celebrate Rainforest Day yesterday in a unique way? Speaking of bringing people together, when we were celebrating the abundance and the diversity of life. Anyone go eat at the Rainforest Cafe? I bet that place was packed. I bet most people didn't even know yesterday was Rainforest Day. No? Anyone take a shower and pretend like you were in the rainforest? No? You maybe put on some sounds of some chirping frogs and jaguars in the background while you're... No? Okay. Tripping frogs. Chirping frogs. Yeah, they chirp. They croak. Yeah, but they chirp. There's some chirping frogs. Look it up. Google. Chirping frogs. Yeah. I think they're called chirping frogs. Hey, higher order derivatives. We've already seen this, haven't we? When we did the calculus book, Falling from the Tower. When we talk about the rate of change of position, we're talking about velocity. When we talk about the rate of change of velocity, we're talking about the acceleration. And if we're talking about how fast they change at an instant, of course, we're talking about their derivatives. So we've seen this notation before, and this single equation connects all three kinematic equations. So we say that A of t, the acceleration equation, is equal to what? V what? How do we read that? V prime of t, which is equal to what? How do we read that? S double prime of t. So that's a higher order derivative. A higher order derivative is just basically going beyond the first derivative, taking the second derivative or the third derivative or the fourth. And there are ways to notate that. If we're just starting with y, then we, of course, we can use y prime, y double prime, and for the third derivative, y triple prime. But once we get past the third derivative, we don't keep putting prime, so we don't say y prime, 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 prime. And the fifth derivative would be prime, 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 like you're playing dominoes. We don't do that. Do you think we switch to Roman numerals like that? I would be for that. If I was at the vote, I would say, yeah, I vote for that. That looks cool. But that's not what we do. We go back to the Arabic numbers. So we write it like that. So if you ever see y with a 4 in parentheses as an exponent, that means the fourth derivative. Okay? The fourth derivative. And in general, we have the nth derivative. If I do it in function notation, it's very similar. We have start with function f, then we had f prime, f double prime, f triple prime, and then we switch to the Arabic with parentheses. Now, if you see something like this, without the parentheses around the 4, does that mean the fourth derivative? No. That means that the function itself is raised to the fourth power, which is why the parentheses are needed. Now, there's a way to circumvent that altogether, and that's just to use Leibniz notation, which I kind of prefer anyway. So if we start with y again, we could say the first derivative is dy dx, and this is how you would write the second derivative. Notice the 2's for second derivative. That's kind of handy. But if you look at that, you might think that it's a typo, right? Does it look like a typo? Like the 2's are in the wrong place. They are actually not. It's d squared y over dx squared. We still read that as the second derivative of y with respect to x, The third derivative would be d cubed y over dx cubed. Here's why. If I start with the function y, and I take the derivative of it with respect to x, the verb, right? Here's the verb. Take the derivative with respect to x. What do we get? We get dy dx. We're essentially just throwing the y into the numerator. But what happens if I then take the derivative with respect to x of dy dx? Well, the derivative of the derivative should be the second derivative. But notice I have d, and y. How many d's do I have? 2. So that's why it becomes essentially what looks like d squared y. And then I have dx times dx, which is essentially dx with parentheses, but we don't actually show the parentheses. So that's why the 2 is offset. We read that as the second derivative of y with respect to x, the third derivative of y with respect to x, and then you don't have to have the parentheses around that anymore. Fourth derivative, and then generally the nth derivative. You could do the same thing with the functions. All right, ready to practice higher order derivatives? Heck yes. Heck yes. Very polite way to say heck yeah. In example 8, y equals that cubic polynomial. I want you to find that. What the heck is y 5 of x? The fifth derivative. Okay. Do you think there's a way to go straight from y to the fifth derivative? Yes. There is, to go straight from y to the fifth derivative. Is there? I don't know if there is or not. But I do know that if I needed to find the fifth derivative, I could take the derivative of the fourth derivative, right? But how do I get the fourth derivative? Take the derivative of the third derivative. But how do I get the third derivative? Take the derivative of the second. So most of the time, and in general, to get to the nth derivative, you have to take the derivative of all the previous n minus 1 derivatives. We call that a recursive relation. You have to generate derivatives recursively. So go ahead and do that. Find y prime, find y double prime, triple prime, the fourth derivative, and then stop at the fifth derivative, and I'll see you there in a little bit. Some of you are already done, okay, because you're doing it while I'm talking, which is fine. I'm going to do it with you. I'm practicing the Leibniz notation. I would say that you could pick whichever one you want. I do expect you to be able to interpret both of them. So if you see both, know what both of them mean. But if you're generating an answer on your own, you can pick your favorite of the two. If you don't ever practice Leibniz notation, though, you're not going to necessarily be used to the offset on the D's. Zach, I guess in hindsight, I could have just jumped straight to the fifth derivative. But hindsight is 20/20, as they say. What does that mean? You don't know what hindsight is 20/20 means? You always have the clarity of retrospection when you look back. Yeah, let's see. Did y'all hit 0 as well? Y'all hit 0? Yeah. And you should expect to do that. If you ever have a polynomial function, you have nice positive integer exponents. The power rule says every time you take the derivative, what happens to the exponent? It gets smaller by 1. So if you start with a positive integer and you keep taking subsequent derivatives recursively, you're going to keep subtracting 1. You should end up at 0. And we do. Now, for a cubic polynomial, we actually hit 0 for the first time on which derivative? The fourth. Ouch. So if we started with the 50th power derivative, we should hit 0 on the which derivative? The 51st, right? So whatever the degree is, you'll hit 0 on the derivative that's 1 larger than that. So, yeah, if you now had x cubed and I asked you to find the fourth derivative or the fifth derivative or anything bigger than 4, you could jump straight to 0 because now you recognize the pattern. That's not true with all functions. All right, we are going to stop right there. We'll do example 9 tomorrow because I don't think we have time to take 447 derivatives, right? That might take the whole period. Zach got off to a good start. You're on like number 225 or something? No? Well, you were doing this problem, no? Yeah. How far did you get? This is a 440. Oh, you got to 5. Okay. We'll pick up there tomorrow. Enjoy the rest of your National Face Your Fears Day.